So we've covered naming of alkynes, but let's compare the physical properties of alkanes, alkenes, and alkynes. Now, as we decrease in total number of atoms, you should expect the boiling point to, or I'm sorry, so as the number of hydrogens decrease, what happens is that the molecules compact more tightly and have more intermolecular forces or higher surface area. So when you go from ethane to ethene, we actually decrease in boiling point. So the mass gets smaller and the boiling point decreases. And then from ethene to ethine, the boiling point, instead of decreasing, actually increases, and that has to do with the increased electronegativity, and so it has higher intermolecular forces. That means the boiling point is going to increase. So the lowest intermolecular force molecule has all single bonds and only carbon and hydrogen. That is the alkanes. So we expect them to be very low boiling. Alkenes and alkynes still have their main force as London dispersion forces, but the pi bond gives it a little bit more polarity because of the negative charge of the pi electrons. And so the intermolecular force for the alkane and the alkenes are similar because one pi bond is not making a huge difference in electronegativity. But when we move to the alkyne and we have 2 pi bonds instead of 1, there's a bigger difference. So we have -42 for the alkane, 3-carbon alkane, -47 for the 3-carbon alkene, and then we go to the 3-carbon alkyne, and there's a higher boiling point by 20 degrees, and that has to do with the polarity of an alkyne because of the pi bonds. So the alkynes have higher boiling points than the alkenes because of the polarity of the pi bond. They have higher London dispersion forces, higher intermolecular interactions. Alkynes. So alkynes actually are going to undergo the same electrophilic addition reactions that we saw in chapter 6. So in chapter 6, we learned that when an alkene, let's draw the corresponding 4-carbon alkene to this 4-carbon alkyne. So when the 4-carbon alkene reacts with HCl, what occurred was the addition of H and Cl to the sp2 carbons, so that one carbon gained a hydrogen until it had 2 hydrogens, and one of the 2 carbons that was a pi carbon gains a chlorine, so that it has a total of 4 bonds. So we eliminated the pi bond, and we gained a hydrogen and a chlorine when we put HCl in solution in reaction with the alkene. The same type of reaction occurs when we include an alkyne with HCl. We will add chlorine and a hydrogen and use 1 pi bond. If we were to use excess HCl, however, if we treat this alkene with another addition of HCl, what would happen? Because alkenes also react with HCl, if I then treat this molecule with reaction arrow HCl, another equivalent of HCl, what's going to happen is that the alkene is then going to add hydrogen and chlorine to the pi bond. And that this occurs such that the positive charge, the carbocation, will be located at the halogenated carbon. So in the first step, we form a carbocation. We add hydrogen, and then we add the carbocation. Now the hydrogen is going to go to the sp2 carbon of the pi bond that has more hydrogens. So it's going, this hydrogen, highlighted in orange, is going to add to this orange carbon because it has more bonds to hydrogen. And then the chlorine, which I'm going to highlight in green, is going to add to the other sp2 carbon that is already bonded to chlorine. So that the intermediate cation has the positive charge on the carbon that is bonded to chlorine, so that the first intermediate of this reaction would be, pen, we need the pen, eraser. We would have CH3, CCl, positive charge, CH2, because I added the orange hydrogen, CH3. So that would be our intermediate cation. And then from there, on the next step, chloride ion, Cl-, would donate a lone pair of electrons to bond to this positively charged carbon. And we would have as a final product CH3, C, Cl2, CH2, CH3. And what that would look like as a skeletal structure is 2 chlorines on carbon 2, and we would get a 2,2-dichlorobutane. Okay, so looking at the mechanism for this electrophilic reaction, and I believe this is on your functional group notebook, let's look at which number it is. Halogenation with halo acid reaction with an alkyne. I think I still have that file open on your page. Nope, that's okay. Go here, go to courses. Oops, come on. Courses. I'm going to pause. So the reaction that we're covering right now in the PowerPoint is number 10, addition of HX, i.e., such as HBr to alkynes, and that is found on page 297 of your text. So we're going to go back to the PowerPoint and continue. All right, so the mechanism of addition. For an alkene, we saw that the mechanism was that the pi bond serves as electron donors to bond to hydrogen, and then the bond between H and Cl breaks and the electrons go to chlorine. We get an alkyl cation and a chloride ion. The addition of the electrophile to an alkyne, if it occurred by the same mechanism, would produce this very stable, very unstable vinylic cation. And so the exact mechanism that this occurs by is not known, but they have a hypothesis about the intermediate. And that this intermediate is not something you're going to be asked about, but you should know that vinylic cations are very unstable. So in terms of carbocation stability, we're going to expand our list, and we're going to say tertiary carbocation is the most stable. And this is not going to be the final list for carbocations. We're going to encounter other carbocations in chapter 8, and the carbocation list is going to expand again. Okay. So relative stabilities, right now our list is that the most stable is a tertiary carbocation, followed by secondary carbocation. And then we have that vinylic cations and primary carbocations are approximately equal. And that's for a secondary vinylic. So a secondary vinylic cation is when a vinyl carbon has a positive charge and the vinyl carbon is bonded to a total of 2 carbons, including the other pi carbon. Then we have that a primary vinylic carbocation is worse than a primary carbocation and approximately equal to a methyl cation. And that vinyl cation, which is a 2-carbon cation with the pi bond between the 2 carbons, is the least stable of the cations we're looking at from this point. So vinyl cations are less stable than tertiary and secondary cations. And we already saw that primary cations pretty much do not form when we were doing the reactions in chapter 6. We were always picking secondary and tertiary carbons over primary carbons to carry a positive charge. So what happens if we don't form a vinyl cation? What is the hypothesis? The hypothesis is that in the transition state, we form something called a pi complex. And so this is the proposed intermediate, and it cannot be proven. This is only theory. And you won't be asked about this theory on the test. Okay. What you do need to know is that when we add HCl to a triple bond, the hydrogen and the chlorine must add through anti-addition. So we're adding HCl across the pi bond. Hydrogen, if the carbons are equally substituted, then there's no difference where the H is added versus the Cl. If the carbons are unequally substituted, that will be a different story. The only time that we have an unequally substituted alkyne is as an internal alkyne versus a terminal alkyne. So here is an internal alkyne. So the pi bond is internal. That means that both of the carbons have a maximum of 2 bonds to carbon, and they are secondary. So both pi carbons are secondary. Both pi carbons have 2 bonds to carbon atoms. Then the terminal alkyne, so both pi carbons are equal for an internal alkyne, would be when we have the triple bond as the last atom, or the last or the first atom in the chain. So here's our example. Now we have 1 carbon that is bonded to only 1 other carbon atom, so that's primary, and 1 carbon that is 1 pi carbon that is bonded to 2 other carbons, and so it's secondary. So now we have a difference in the substitution of the vinyl carbons for our alkyne, and that means that it will matter where the H adds and where the Cl adds, and the rules will be the same. The hydrogen will add to the less substituted carbon, and the chlorine will add to the more substituted carbon for a terminal alkyne. Now, there is a slide about this in later in this PowerPoint. It's either the next slide or it's later on in the chapter. Okay? But that's just an introduction to the topic. Okay? So for an internal alkyne, both of the carbons are going to be secondary. And so what's going to occur is that we could get multiple products if the alkyne is not symmetric, for one thing. But also, we have a rule, and this is would be one of your key points for this reaction. The hydrogen that adds to a vinyl carbon and the chlorine that adds to a vinyl carbon must add by anti-addition, so that the H and the Cl are on opposite sides of the pi bond. And this is further evidence that the pi complex forms, because whenever we form a three-membered ring, then the addition of a second atom to the molecule has to come from the side of the ring that is opposite to where the other atom that forms the three-member ring is located. Okay, alkynes are less stable and less reactive than alkenes. So they have a lower stability, which means that the initial energy of the reactant is greater than an alkene reactant. Okay, so alkyne reactant is higher energy higher initial energy than alkene reactant. Okay, so putting this in more simple terms. The other thing that they are saying is that the alkyne reactant will have a higher transition state energy than the alkene reactant. So TS energy, the alkyne is greater than alkene. And that means that alkynes are going to take longer to react, because the greater the transition state energy, the longer the reaction requires. Okay, and the difference is always such that the alkene overall is going to be both the product of the alkyne and the reactant of the alkyne are higher energy than the alkene in terms of the formation of the intermediate step. So this is higher energy than the alkyl cation. All right. Whew. So when we have HCl with an alkyne, usually we're using it as a solvent. What that means is that HCl is present in excess of the alkyne. So if we have 1 mole of alkyne and maybe 2, 3, 4, 5 moles of HCl, then we have excess HCl, and HCl will react twice. And what this does is that if we have a 1-to-1 ratio, so only if we have, so if 1 mole alkyne to 1 mole HCl, then only one Cl is added. But if 1 mole alkyne to 2 moles HCl or excess HCl, then 2 Cl's add. Okay, and so that's a very important distinction, right? We're going to end up, if we have a 1-to-1 ratio, okay, we add 1 chlorine and we stop at having an haloalkene, right? So this is a haloalkene in functional group. And if not, if we have excess HCl, then we're going to get what we call a geminal dihalide or a geminal dihaloalkane. And I told you before what geminal meant. Geminal dihaloalkane. Okay, and what geminal means is that both of the halogens are on the same carbon. So geminal. 2 groups of interest on same carbon. Okay, so the reaction of an alkyne with excess HCl gives us a geminal dihalide, and your homework is going to be very specific. They're either going to have a 1-to-1 ratio of the alkyne to the HCl, and they may say 1 mole, or they may not say 1 mole. They may just, because it should be understood that there's a 1 there, expect you to know that only 1 adds. And then when they want you to know that it goes to excess HCl, they will actually label it XS, or they will label it as 2 moles of HCl, and that's when you're going to carry it all the way through to the geminal dihalide. So this reaction can be stopped by the addition of very specifically 1 equivalent of Cl. And the reason that we can stop after 1 equivalent of Cl, which means 1 mole to 1 mole, is because a halo-substituted alkene has less nucleophilicity than either an alkene or an alkyne. So what they're actually saying by relative reactivity is that we're going from more nucleophilic to less nucleophilic. And a nucleophile has to have the ability to donate electrons. So what happens, why the vinyl alkene is less able to donate electrons, is because the chlorine is drawing electrons to itself. So that pi electron density is going to chlorine, then there is less pi electron density available to donate to make a new bond. So we have to have excess HCl to make having a new bond more favorable. So less nucleophilic literally means less able to donate electrons. And that is because of the thief chlorine. And all halogens are thieves, taking away electron density. Okay, the addition to a terminal alkyne. I told you this was coming. So now the carbons are unequally substituted, and we're going to obey the same rule that we obeyed in for the reaction of an alkene that was unequally substituted with HCl. The hydrogen goes to the less substituted carbon. So we have a primary carbon and a secondary carbon. And the chlorine goes to the more substituted carbon. So that means that we're going to end up with hydrogen at the red carbon, which is only primary, and chlorine at the blue carbon that is secondary. So we have a primary carbon and a secondary carbon. And notice, this is understood that we have one equivalent. We don't have to draw a 1 in front, but if they're writing a balanced equation, you should know that there is a 1 there, that it's 1 mole. Unless they specifically tell you that there is excess or more than 1 mole of HCl. Okay? Please notice that the substitution of the carbons did not change by the addition of hydrogen or chlorine. Substitution of a carbon indicates number of bonds to carbon, and we didn't bond any new carbons. So we still have a primary carbon and a secondary carbon. Okay, the mechanism for the electrophilic addition is shown here. And what we're doing, so the pi electrons are donated to the hydrogen, and the bond between hydrogen and Cl breaks. That produces chloride ion and our pi complex. So that the pi electrons form this 3-membered ring, even though there are only a total of 2 pi electrons there. Chlorine is going to be shown to donate a lone pair to the more substituted carbon. And at that time, the electron density of the pi bond is going to go fully to the H, and all other electron density between H and Cl is going to have electron density going to hydrogen and to the chloride. So this is a partial bond and a partial bond. It's a very strange looking mechanism, but go ahead and make sure to put this in your functional group notebook. The final product for the addition of this one equivalent gives us our haloalkene with chlorine on the more substituted carbon. Okay? So if there is a positive charge, it is more stable to have that positive charge on the secondary carbon, even if it's bonded to chlorine, than it is to have the positive charge on the primary carbon. So the more stable transition state has chloride ion bonding to the secondary pi carbon.